Hey everybody, your Friendly Math Tutor here with our Unit 4 Part 1 lecture. So as we enter week 4 of this course, some of these topics have a lot of information in them or are more heavily tested on the AP test. So we're going to go into a little bit of a deeper dive. So today we're going to do Unit 4, and next week we'll do also Unit 4, where we'll go over similar problems, but maybe have a couple of wrinkles here and there. And the next couple units, we're going to spend 2 weeks on each unit. All right. So as always, make sure you subscribe. You can like this video. Check out our TikTok for all the problems the next 2 weeks that are related to Unit 4, Instagram, Facebook, and Patreon for all of the extras that we throw on there. All right. So let's dive in today. So Unit 4 is what's called Contextual Applications of Derivatives. And one of those applications is going to be straight line motion. So we're going to go through an example right now of a straight line motion problem. So basically what these are is, you just imagine you have this particle that's moving back and forth. It can only go two ways, left or right. And S of t is what they're going to give us. This is going to be a position function. What this function does is it tells us the position of the particle on the x-axis at any time t. So if I want to know where the particle is after 5 seconds, plug in 5 here, I get a number that tells me where it is. And this particle is just going to keep moving back and forth. What we're going to do is go through kind of all the different questions that they could ask you about a straight line motion problem. So the first is, what's v of t? V of t is the velocity function. And the thing we have to understand is that velocity is just the rate of change of position. So it's just the derivative. So the derivative of position is velocity. So we're just going to use some basic differentiation here. So 3t squared minus 12t plus 9. So that is the velocity equation. So now what that tells us, if we want to know the velocity at any time, I just substitute in, say again, like 5 seconds, and I'll know its position after 5 seconds, and then I'll also know what its velocity is, its rate of change at 5 seconds. And then A of t. A of t is the acceleration. Acceleration is the rate of change of the rate of change. So it is the derivative of velocity or the second derivative of position. So this simply here is just 6t minus 12. All right. So another thing that they'll ask you is this idea of displacement or net distance. So displacement is just basically how far away does this particle end at a certain time relative to where it started. So let's go back up here and give ourselves an interval. So let's say we're just looking at from 0 seconds to 7 seconds. Whoops. Well, let's make sure we include that. So we want to kind of take a look at, well, during that first 7 seconds, where did this particle end up relative to where it started, right? So that's its displacement. So what we can do is simply just find two things for displacement. It's going to be where did it end up minus where did it start. And notice I'm plugging into the position function for these two values. So S of 7 is 117, and S of 0 is pretty easy to see. That's just 5. So its displacement is 112 units. And again, what that means, since it's positive, it means the particle ended up, after 7 seconds, 112 units to the right of where it started, all right? Displacement can be negative. It just means you ended up to the left of where you started. And just a reminder, straight line motion, we're only looking at left and right, all right? They're the only motion that we're looking at for these types of problems. So now let's keep going and take a look at total distance. Now, that displacement is different than total distance because you can imagine if I go here and then I turn around and I go back here, my displacement is 0. But my total distance is certainly more than that. It's double what I walk this way. And so what we want to do is, well, where could this particle have turned around? So every time the particle turns around, it's going to have a zero velocity. It can't go from positive velocity, which is moving right, and negative velocity is moving left. It can't go from positive to negative velocity without being zero for an instant. So what we want to do is, well, where did this particle stop? Where did it have zero velocity? Well, the velocity equation is going to tell us that. So what we're going to do is take the velocity equation and set it equal to zero. I'm also going to factor this a little bit. So we'll do 3 times t squared minus 4t plus 3 equals 0. And then I can factor this. So t minus 3 times t minus 1 equals 0. So at t equals 3 and t equals 1, the particle stopped, possibly turned around, and started racking up a total distance bigger than its displacement. So we still need to know, well, where did it start? S of 0. And we now know from before that that's 5. We want to know where was it after 1 second, because it stopped there. We also want to know where was it after 3 seconds, because it stopped there. And then where was it after 7 seconds, because that's where we're kind of ending this problem. All right, so after 1 second, it's at 9. After 3 seconds, it's at 5. And 7 seconds, we figured out, was 112. So now the way that we find total distance is we just add up these numbers. So it went from 5 to 9. That's a distance of 4 units. It went from 9 back to 5. That's another distance of 4 units. And then it went from 5 to 112. That's a distance of 107 units. So altogether, it went 115 units. So all of that, add that, and you get a total distance of 115 units. Okay, so the next thing we want to take a look at is, when is the particle moving left and moving right? Well, what we want to do is we want to take a look at a number line representing the velocity. And actually, I'll get rid of this. We're really going to look at from 0, and let's just keep going. Let's go past the 7 for this one. But we want to start at 0 because 0 is time. And we know that it stopped at 1 and it stopped at 3. So I'm going to put those on the number line. So between 0 and 1, let's say 0.5. If I substitute that in here, I'm going to get a negative times a negative, which is going to give me a positive. So that means it has positive velocity during the first second. And then between 1 and 3, let's say I choose 2. Well, 2 minus 3 is negative. 2 minus 1 is positive. A negative times a positive is a negative. So between 1 and 3 seconds, it has a negative velocity. And finally, pick a number bigger than 3, and you're going to get 2 positives. So it's going to have a positive velocity again. So that means it's moving right from 0 to 1, and then again from 3 and on. And it's moving left whenever it has negative velocity between 1 and 3. Now notice at 1 and 3, the particle is stopped, so it's not moving right or moving left. All right. Finally, we're going to look at speeding up and slowing down. Well, this is related to the acceleration. So again, we start at 0. Well, the acceleration, we can easily see, well, where is the acceleration 0? Well, that's just going to happen at 2 seconds, right? We can easily set this equal to 0, and we're going to get 2 seconds. And to the left of 2, let's say 1 second, we're going to get a negative acceleration. And to the right of 2, we're going to get a positive acceleration. Right, so just substitute those numbers into the acceleration. Now, it's unfortunately, so let me put these over here. So speeding up and slowing down, we're going to put these intervals. Unfortunately, it's not as easy as just saying, oh, well, wherever this is negative, it's slowing down, and where this is positive, it's speeding up. It doesn't work that way. Speeding up and slowing down takes into account both the velocity and acceleration. So in order for something to speed up, the velocity and acceleration have to have the same sign. They have to either both be positive, so velocity is positive, it's moving to the right, and then positive acceleration speeds that up. But if something is moving left and acceleration is negative, that's going to also speed it up in that direction. Just imagine if I were to launch a chair out of this window. It would definitely have a negative velocity because it would be moving downward, and it would obviously have a negative acceleration. Gravity is always a negative acceleration, pulling something towards Earth. And the chair would certainly be speeding up as it goes towards the ground, all right? So if you have positive velocity, positive acceleration, or negative velocity, negative acceleration. So when you get a sign match, that's speeding up. Slowing down is going to occur when you have opposite signs. So if we look at speeding up is where they're the same sign. That's going to first occur from 1 to 2. They're both going to be negative, all right? So from 1 to 2. And then they'll both be positive from 3 to infinity. And slowing down is where they have opposite signs. So that's going to happen from 0 to 1. We're going to have positive velocity, negative acceleration. And then again from 2 to 3, we're going to have negative velocity, positive acceleration. So that's how we do, again, left, right is just sign of velocity. Speeding up, slowing down takes into account the sign of velocity and the sign of acceleration. Sign match is speeding up, all right? Okay, let us move on. Hey everybody, before we do move on, I just realized that I made a mistake. So some of you watching this might have hopefully caught this mistake. What I did was over in the total distance for S of 7, I wrote 112. Well, I looked back at the displacement. S of 7 is actually 117. So that's going to change just a couple things here. What that's going to do is this becomes 117. So these are both still 4, but now this one is 112. So when I do 4 plus 4 plus 112, that gives me 120. All right, so the total distance should have been 120. So I hope some of you that were watching this and saw that mistake were yelling at the screen saying, what are you doing? All right, well, here we've corrected it. So hopefully that makes sense. All right. All right, let's move on to the next contextual application of derivatives, and that's related rates. We're going to go over 4 problems. In the next week's lecture, we'll do even more. So for right now, let's start with the quintessential related rate beginner problem, which is the ladder problem. So we got a 13-foot ladder that begins to slide down a wall at a rate of 2 feet per second. So I'm going to try to model this out here. So we've got this ladder that is the hypotenuse of a right triangle and begins to fall down the wall. So what happens is, as the ladder begins to fall, this distance is going to change. So I'm going to call that y. Also, as the ladder falls, this distance here, its distance from the base of the wall, is also going to change. But as the ladder falls, and this is one of the most important pieces of related rate problems, is what is a variable and what's a constant. So as the problem moves through time, think about what lengths or angles or whatever we're looking at, what is changing and what's not. The ladder itself, the 13-foot ladder, that's not going to change size, all right? So that hypotenuse is always going to be 13. We do not want to call that a variable because it's not. It's a constant in this problem. But this, the y and the x, even though when it's 12 feet from the base, at a moment this is 12, but we don't want to call that 12 because it is changing, all right? So the x and y are changing and the 13 is not. So now what relates these is Pythagorean theorem. So x squared plus y squared equals 13 squared. And then we could take the derivative, so this is related to implicit differentiation, but we're going to take the derivative with respect to time, all right? So the derivative of x squared is 2x dx dt. Remember implicit differentiation. The derivative of x, and then again, remember that x is some now function of time, how it changes through time. So dx dt is the derivative of x. So again, we're like doing the chain rule. So the derivative of y squared in related rates is 2y dy dt, right? Because we're taking the derivative with respect to time as opposed to with respect to x. This is what we were doing before. And the derivative of 13 squared is just a constant, so that's 0. So now we go in and we start to think about, well, what are they asking us to find? First, I can just ignore the 2's. I can divide that out. It begins to slide down the wall at a rate of 2 feet per second. That's this. So that's how y changes. So this dy dt is -2. All right, very important. It's sliding down. This distance is getting smaller, so the rate is negative. And then how fast is it moving away from the wall when it's 12 feet from the base? So that's x is 12. So this is 12. How fast is it moving? That's dx dt. Now, what is y? They don't give that in the problem. So you got to go back to your original diagram, and now imagine that this is 12, just for that moment. This is always 13, so this we could just use Pythagorean theorem, or if we remember our Pythagorean triples, this is just a 5, 12, 13 triangle. So out of that specific moment, even though y is changing, at that exact moment, it's 5. So that goes here. All right, now I have a pretty easy problem to solve. 12 dx dt equals, so this is -10, throw it on the other side, so you get 10. So dx dt equals 10 over 12, which is 5/6. And our unit of measurement here is feet per second. And that is our answer. It makes sense that it's positive because as the ladder falls, this distance is getting bigger. Okay, let's take a look at another problem that also involves the Pythagorean theorem, also involves the fact that there's a constant, but in a different place. So this is a really important thing when we do related rate problems. So we've got a baseball diamond as a 90-foot square, or 90 feet square. A runner from first base to second base runs at 25 feet per second. How fast is he moving away from home plate when he's 30 feet from first base? So if we try to imagine a baseball diamond, which again is really a square. So this is home plate, this is first base, and this is second base. Anybody who may not know a lot about baseball, this is our diagram. The runner is somewhere here, so as they run from first to second, their distance from home is changing. All right. Now what happens is we got another right triangle. This distance from home to first, well, that's always 90 feet. That's not going to change. So that is going to be 90. The distance from first to second, well, that's changing. The runner is running, so their distance from first is increasing. So I'm just going to call that x. And then the distance from home, we can call it anything we want. I'm just going to call it y, but you can call it whatever you'd like. So therefore, now our Pythagorean theorem looks like this. 90 squared plus x squared equals y squared. All right, so notice the difference between this Pythagorean theorem and this. They both have a constant in it, but the constant is in a different place. Here, the constant is the leg that's not changing, and here, the ladder is the hypotenuse that's not changing. So if we say the derivative with respect to time, the derivative of a constant is gone. The derivative of x squared is 2x dx dt, and the derivative of y squared is 2y dy dt. 2's cancel again. X represents this distance. Well, they tell us that. How fast is he moving away from home plate? When he's 30 feet from first base. So that's 30 feet. dx dt is the rate at which x is changing. Well, that's the runner running, so that's 25. And as the runner runs to second base, its distance from first is increasing, so that's going to be a positive rate. Now we need y and dy dt. Well, dy dt is how fast he's moving away from home plate, so dy dt is what we're looking for. Now we need to know y when this is 90, as it always is, and this distance here is 30. All right, so we can just do Pythagorean theorem. So we can do 90 squared plus 30 squared equals y squared. I guess we could just use a calculator for that. It looks like, 90 squared plus 30 squared is 9,000. So the root of 9,000, I'll use a decimal here. It's about 94.87. So that's gonna, I need a little more room. That's gonna go here. So we got 94.87 times dy dt. And now I can just divide. So dy dt, the rate at which it's changing from home plate, we are going to just get 30 times 25 divided by 94.87 gives us 7.9. And that is in feet per second. All right, so here, just again, look, we've got two Pythagorean theorem problems, both of which have constants in them, and those constants are in different places. It's a really important part of related rate problems as we set them up. All right, now we're going to move on to a couple other different types of related rate problems. All right, let's move on. So first we're going to do another Pythagorean theorem problem. This one is going to have a slight wrinkle in it, and then we'll get to the typical cone problem. All right, so this one, car A is 100 miles east of car B. At noon, car A drives north at 60 miles per hour. At 1 p.m., car B starts driving east at 70 miles per hour. How fast is the distance between them changing at 2 p.m.? So let's try to model this a little bit. So car A is 100 miles east of car B. So we've got car A here. It's east of B, so B is here, and this distance is 100. At noon, car A drives north. So car A starts to drive north. At 1 p.m., we'll deal with that time later, car B starts driving east. So car B starts going this way. And how fast is the distance between them changing at 2 p.m.? So we're basically going to be looking at this problem. All right, so now notice kind of what we have here. We've got a distance that's changing. So I'm going to call that x. We also have this car A is driving this way. So car A is, this distance is changing. I'm going to call that y. And obviously the distance between them is changing. That's what we're looking for. So I'm going to call that z. So the wrinkle here is that we've got a Pythagorean theorem problem that has three things that are changing. So we are going to have x squared plus y squared equals z squared. And then we can take the derivative with respect to time. So 2x dx dt plus 2y dy dt equals 2z dz dt. Cancel the 2's as always in these Pythagorean theorem problems. And now we get into where we need all the information and kind of how we look at it. It's going to be really important. So x represents this distance at a particular time. So let's focus on car B. Car B starts driving east at 1 p.m. and we're analyzing this problem at 2 p.m. So we want to know what's going on at 2 p.m. Well, car B has driven for an hour, which means it's traveled 70 miles. It's traveling 70 miles per hour. So in 1 hour, it goes 70 miles. So it went 70 miles, but it started, this distance was 100 and it went 70. So I know this proportion is a little off, but again, diagram not drawn to scale. So this is 70. So this distance that it still has to travel is going to be 30. So x is 30. dx dt is the rate at which that's changing. Well, that's just the speed of the car. So car B is driving 70 miles per hour, but actually it's not speed because our distance is getting smaller. So I need to make that negative. So this is negative 70. Now y is this distance. So now we look at car A. Well, car A started at noon, drove north at 60 miles per hour, but since it's 2 p.m. now, car A's been driving for 2 hours, so it traveled 120 miles. dy dt is just the rate at which that side is changing, so that's car A, so that's 60 miles per hour. Now z we're going to have to find, and dz dt is what we're looking for. Well, z we're going to have to find just using the Pythagorean theorem. So I will get my calculator here. We're just using the 30 and the 120. So this distance is 30, this distance is 120, so I'm going to do 30 squared plus 120 squared, and I'm going to take the square root of that, and it's about 123.69. All right, so that's the z distance at the exact moment that this distance is 30 and this distance is 120. So when there's a value that's unknown at one of these specific values, like one of the variables in the derivative, going back to the original equation is going to be how you're going to solve for that when they don't give it to you in the problem. And then again, we'll go back to the calculator and we can easily just solve for dz dt. So I can do 30 times negative 70 plus 120 times 60, and then divide all that by 123.69, and we get 41.23. So 41.23 miles per hour is dz dt, which is what they asked us to find. That's the distance between them. That's the rate at which the distance between them is changing. So the fact that it's positive tells us that that distance is actually increasing right now. All right. So that kind of ends for today as far as what we're going to do with the Pythagorean theorem problems. The other thing I wanted to go over is this cone problem, and then next week we'll take a look at maybe some other kind of related rate problems that we could see. So as far as this is our typical cone problem. So we got a conical cup. So we've got some cup that's shaped like a cone, and the cup itself is 4 centimeters across. Well, to me, what's more important is that it's a 2 centimeter radius. That's 4 centimeters across. And then it's 6 centimeters deep. So it's 6 centimeters deep, all right? Water's leaking out of it. How fast is the water level dropping when the height of the water is 3 centimeters? So there's the water in there. All right, so we've got some water in there, and then water is coming out the bottom. So what happens is we kind of have 2 cones in this problem. We have the cone that is the actual cup, and then the water in the cup takes the shape of the cone. So the water itself kind of is a different cone that's inside the other cone. And the reason that's important is because the cup itself never changes, but the water inside the cup is leaking out. So that cone inside the bigger cone is getting smaller and smaller and smaller. So let's take a look at the cone of the water that's changing. The volume of the cone is 1/3 pi r squared h. So pi r squared h is just the volume of a cylinder, and a cone is always 1/3 of that cylinder. So we can take, actually no, we don't want to take the derivative. This is why I wanted to go over this problem. If we do take the derivative, we've got v, r, and h. When we take the derivative, that means we'll have a dv dt somewhere, a dr dt somewhere, and a dh dt somewhere. 3 rates. In the problem, they give us 1 rate. Notice the little cube up there, that's cubic centimeters. That tells us that that's dv dt. Then they ask how fast is the water level dropping. The water level is the height, so that's dh dt. So dh dt we want to look for, but there's no mention of dr dt. So we don't want there to be a dr dt because then we'll have too many variables, too many unknowns. So what we want to do is we want to make a substitution. We don't want r to be here. So we make that substitution by doing similar triangles. So what we have here is, just imagine you've got this triangle. Again, this is what I was talking about, the cone inside of a cone. It might have sounded strange, but a strange way to look at it. But what it is the water has a radius r and a height h, and they're both getting smaller. But the cone, the cup itself, isn't changing. But they have a relationship, and the relationship is similar triangles. So r over 2 should equal h over 6, always. All right, so as r and h change, they will always follow this proportion. I can do some cross multiplying, so 6r equals 2h, r equals 2/6, which is 1/3 h. Now notice I'm solving for r because I'm going to replace r with the 1/3 h. Now r is gone, and when I take the derivative, I won't have to worry about dr dt. I'll have a dv dt and a dh dt. I know dv dt, I'll be able to solve for dh dt. All right, so when you have too many variables, like back here we had 3 variables, nothing wrong with 3 variables, but I was given 2 rates. Here, 3 variables, only given 1 rate, that's an issue, right? That's just an algebra issue. So we fix it by doing substitution. So I'm gonna do a little bit of simplifying here. So this is 1/3 h squared times h. Again, it's more simplifying, so I got 1/3. 1/3 squared is 1/9, and 1/9 times 1/3 is 1/27 pi. H squared times h is h cubed. So now what I have is the volume of the water inside of this particular cone, and this is the volume based only on h, which is what we want. Take the derivative with respect to time, so dv dt equals 1/27 pi times 3h squared times dh dt. Now let's plug in. So it's leaking out. So the cone that is the water inside is getting smaller. So that is a -2. 3 over 27 is 1/9. H is when the water level is 3, so 3 squared is 9 dh dt. Well, this is nice. The 9 and the 1/9 cancels out, so I can go over here. So finally, dh dt, the rate at which the water level is dropping, is going to be -2 over pi, and that should be in centimeters per second, because we're back down to a single dimension, not 3-dimension volume. Be very careful if this were some multiple choice question. So mathematically, we should get a negative because the water level, the water's leaking out. So the height is getting smaller and smaller and smaller. So mathematically, we get the answer -2 over pi. But if to technically, like semantically, to answer the question, it says how fast is the water level dropping? The answer to that question would be it's dropping 2 over pi. All right. So if this were a multiple choice question and it said, how fast is the water level dropping? The answer would be 2 over pi, not negative, because the dropping is the negative. It gets a little tricky with problems like that, all right? I'm going to just kind of focus on the fact that mathematically we get a negative, and that negative means that it is dropping, all right? Okay. All right, let's keep going. So 2 more applications of derivatives, contextual applications of derivatives. And the next one is local linearity. So what that means is, let's say we have a curve, and I'm going to pick a point on that curve. And that value, that specific x value, I'm going to call a. And the y value, when I plug it in, is simply just going to be f of a. So we're going to call this curve f of x. What local linearity is, like the word local just means nearby, and linearity means line. So if I make a tangent line, which we've learned how to do, if you zoom in right here, locally, right, in the nearby, in the neighborhood of the point A comma f of a, this line, which is kind of a poor excuse for a line, but if this were a very good line, that line would be just in this area, very close, a good approximation of the curve. Down here, pretty terrible. Up here, as we go further, they diverge from each other. But in this local neighborhood, this line and this curve are almost the same thing. They're very close. So we're going to use this idea of local linearity to approximate, we're going to use the line instead of the curve. And I want to show you, there's this thing called a linearization formula, and sometimes it's taught in such a way where it's just like, well, here's this L of X formula and use the formula. But I want to kind of show you that it is a formula that you're very familiar with. It's just in disguise, all right? So you don't need to memorize this formula. Most of us, but if we get to this level, we know the point slope formula from algebra. And that is simply just y minus y1 equals m times x minus x1. Right? We know this. This is in our brains. There's no reason to memorize something else and store it in a different part of our brain. Just think about this, and I'm going to show you where this linearization or local linearity equation comes from. So what we're going to do is this y is going to become the y value of some x value that's near a. So let's say we've got this x value here, all right? And we go up, and the idea is that point is close to the actual point. So we're going to approximate this y value with the y value from the line. So that y value, instead of f of x, we're going to call it L of x. This y1, I'm going to move to the other side, all right? And what that y1 is, our x1, y1 is the point right here. That is the point a comma f of a, all right? So this point here is a comma f of a. Well, if I do, so that means y1 is really f of a, but I'm adding it to the other side. Now I got m. Well, m is the slope of the line. And I hope that by now we all know that the slope of a line, a tangent line at a specific point, is just the derivative evaluated at that point. So that is f prime of a. So f prime of a is just this slope. And then I have x. X is the one thing that kind of stays itself in this problem. It's just some random x value that's near a, minus x1. Well, x1 is a itself. This is our x1, y1. So if you were presented this equation just as, oh, this is the linearization or the local linearity formula, it might look fancy and complicated, but it is literally the point slope formula from Algebra 1, where our point is a comma f of a, y we're giving this fancy name L of x, and the slope now, instead of getting it from 2 points like in Algebra 1, we're getting it from 1 point, which is just the derivative evaluated at that point. All right, so now what I'm going to do is I'm going to show you how to use this formula to actually, put it in action. So let's say we wanted to approximate 2.01 squared. Well, we need a function first. So we're going to say our function is just x squared. Then we need an a value. An a value is a value that you can evaluate this function with that's near where we're trying to approximate, that you can just do in your head. I think it's pretty obvious that it would just be 2. I hope we can all do 2 squared in our head. So a is 2. And x is the value that, at least the x in this formula, is the value that we're trying to approximate. So that's 2.01. So we're trying to figure out, well, if I were to plug in 2.01 squared in for x, what would that approximately equal? And we're going to use this formula, which this formula never has us plug in 2.01. It actually has us plug in a instead, which is 2. And we could do that because it's much easier. It's easier to use 2 than it is to use 2.01. If we could just do 2.01, we wouldn't be doing this problem, right? So I am going to first find my linearization equation. So f of a is plugging in 2 into our function, which is 4. F prime of a, well, I can easily find f prime of x, which is x squared, derivative of x squared is 2x. Plug in 2, that also gives us 4. And x minus a, right? Well, right now, we're not gonna make x this yet. I wanna keep my notation correct. So for now, let's just say it's x. And a is 2. So what I have is my local linearity, or my linearization, around this point 2, 4, right? And then I can use that to approximate any value that's close to 2. The key is that it's close. A value out here would not be close, but a value inside this little neighborhood is close. Well, 2.01 is objectively close to 2, right? So now I'm just going to substitute that in. So now, using my equation that'll work for any point that's close to 2, I'm going to substitute in 2.01. So I'm going to get 4 plus 4 times 2.01 minus 2. Keeping it in this form and not using slope-intercept form there's a reason for it. It's going to make the calculation much easier because you're going to do this first, and this is clearly just 0.01. Then that's 0.04, and 0.04 plus 4 is 4.04. So 2.01 squared is approximately 4.04. And if I actually do that in the calculator, it's 4.0401. So it's like 1/10,000th off, which is pretty close, right? So to think about the power of that, we're using a line to just approximate a curve, a completely different function, and it gets us that close. All right? All right, let's move on to our last contextual application of derivatives, and that is L'Hopital's rule. So the limit as x approaches a of f of x over g of x. So if we're taking the limit as x goes to some value of a rational expression, I guess it doesn't have to be rational, just any fraction that has a function of x over another function of x. If you substitute x equals a, all right, so remember the first step in limits, go back and watch the first video in limits, and you'll notice that the first thing we should always do is substitute that in. When we substitute that in, if we get one of two cases, if we get 0 over 0 or infinity over infinity, we can use something called L'Hopital's rule, which says that if you take the limit as x approaches a, but instead of doing this function over this function, we do the derivative of this function over the derivative of the denominator function, that gives us the same answer. These things are equivalent. And then this can keep going. If I do it again and I get 0 over 0 or infinity over infinity, I can do it again. All right. So we couldn't have done it in unit 1 because we didn't know how to take derivatives yet. But now that we know how to do the derivative, it becomes an application of the derivative. So just to show you 2 quick examples, and then again, next week we'll do some more challenging examples. So this is kind of just an intro to this. So if we take a look at the limit as x goes to pi over 2 of cosine squared x over sine x minus 1. Well, direct substitution is how we should get started. The cosine of pi over 2 is 0. The sine of pi over 2 is 1, and 1 minus 1 is 0. So 0 over 0 is in indeterminate form. So what we want to use is L'Hopital's rule. So we are going to keep the limit as x approaches pi over 2. The derivative of the numerator, let's use the chain rule. So it's 2 cosine x to the first times the derivative of cosine x, which is negative sine x. Derivative of the bottom, derivative of sine x is cosine x. The derivative of 1 is 0. And then I always simplify. I'm sure there's an exception to this rule, but I usually think in my head, always simplify like algebra before doing calculus. So before plugging in again, just get rid of this. All right. Now I substitute in pi over 2. Sine of pi over 2 is 1. Negative 1 times 2 is negative 2, which is an actual real number. So that's the answer to our original limit. All right. Last problem. The limit as x goes to infinity. Well, you don't really plug in infinity, but if we analyze this at infinity, we've got a polynomial that's just going to grow infinitely larger. On the bottom, we have this part is like a line, and then we have an exponential function. Everything here is just going to grow without bound. So we can say that the numerator goes to infinity over the denominator, which is infinity. So we're going to take the limit as x goes to infinity, and let's use L'Hopital's rule. Derivative of the numerator is 3x squared plus 6x plus 8. The derivative of the denominator is e to the x plus 3. But I still have an infinite limit over an infinite limit. So I'm going to take the limit as x goes to infinity, and I'm going to do it again. So I'm going to get 6x plus 6 over just e to the x. And unfortunately, I still get infinity over infinity. And I think finally what happens is I end up with 6 over e to the x. Well, I no longer get infinity over infinity because the numerator limit now goes to 6, because the limit of a constant is the constant itself. So I get 6 over infinity, and 6 over infinity is 6 divided by an infinitely large number, which is going to get closer and closer to 0. So now 0 is an actual real number, and that is our limit. So I wanted you to just see how we can apply L'Hopital's rule in our two basic cases. Everything that we went over today was kind of the intro type problems to all of our contextual applications. Next week's video, we'll kind of go over the same topics, but I'm going to try to find some kind of like next level problems. All right. So I hope that was helpful. Again, check out all of our content throughout the week, and I will see you next week for the second video on this unit. All right.